The cosmos appears as a beautiful, seemingly chaotic expanse of scattered stars. Yet hidden within that apparent randomness is a profound and intricate architecture. This is the hidden design of galaxies, the grand pattern woven into the fabric of the universe itself. By the end of our journey, you will see the night sky not as a random splash of light, but as a decipherable map of cosmic order. We will uncover how unseen forces and mathematical relationships sculpt entire galaxies from what looks like endless complexity. What does the silent, subtle presence of dark matter have to do with the graceful spin of a spiral galaxy? How can a faint whisper from the earliest moments shape where galaxies will form billions of years later? When you look up at the stars, what kind of harmony do you hope to find? For thousands of years, that celestial canvas presented humanity with a beautiful mystery. Our ancestors looked up and saw not a blueprint, but a scattering of bright points with no obvious plan. They connected these stars into patterns, telling stories of gods and heroes, but these constellations were a human way to make sense of cosmic wonder. The deeper structure of the galaxy itself remained entirely out of view. Even as the first telescopes turned skyward, the view only deepened the initial sense of awe. Those distant, hazy patches of light called nebulae seemed to confirm a universe of glorious, untamed variety. They were just soft impressions on the lens of reality, hints of something vast and intricate stretching into infinity. This perception of something beyond order was not a failure of imagination, but a testament to the scale of the secret. The cosmos was patiently waiting for us to develop the tools and the perspective to look past the appearance of randomness and perceive the subtle framework holding everything together. The great discovery was not that the universe was simple, but that its profound complexity was itself a form of deep and meaningful order. Gravity is the universe's great unifier, a force that speaks a single, simple command across the vastness of space. Come together, in the profound emptiness following the dawn of time, this command was the first step toward building everything we see. The early cosmos was a nearly uniform sea of hydrogen and helium gas, a formless potential waiting for a catalyst. That catalyst was the subtle variations, the faintest of wrinkles in the fabric of space itself. Where matter was just slightly more dense, gravity had a tiny advantage. It began its patient work, pulling atom toward atom with an embrace that would last for millions of years. Think of a breath on a cold morning, how the invisible water vapor in your exhale is drawn together to form a visible cloud. On a scale so immense it defies human comprehension, gravity performed a similar act of congregation. These gathering clouds of primordial gas were the raw material, the cosmic clay. And gravity was the sculptor, initiating a collapse that would forge the first grand structures in the darkness. This relentless pull did not just create a uniform shape. As these vast clouds condensed, they began to spin, a consequence of conserving the tiny motions inherited from the early universe. This spin flattened the clouds into great, rotating disks, the blueprint for the majestic spiral galaxies we recognize today. It is a dance that starts with a whisper, a gentle tug that grows into a whirlpool of creation, setting the stage for the birth of billions of stars. Every galaxy, from the most graceful spiral to the most ancient elliptical, owes its very existence to this foundational act. It is the initial stroke of order upon the canvas of chaos, the first and most critical piece of the puzzle. Without this silent, universal architect, the cosmos would remain a formless, dark, and silent sea. But for gravity to sculpt a galaxy, it needs something to hold onto. This is where the true hidden architecture reveals itself, a framework made of a substance we cannot see. Dark matter is the invisible scaffold. While gravity acts as the force that pulls everything together, dark matter provides the essential structure, the form that dictates where a galaxy will form and how it will behave. We cannot observe it directly with any telescope because it does not emit, absorb, or reflect light. Its presence is known only by its subtle gravitational influence on the things we can see. Think of a marionette, a puppet dancing gracefully on a stage. You see the puppet, the visible star, moving through its performance, but the motion is impossible without the unseen hands and strings guiding it from above. Dark matter is that unseen guide for entire galaxies. The most compelling evidence for this hidden framework comes from the way galaxies spin. Based on the amount of visible matter, the stars and gas at the outer edges of a spiral galaxy should be moving much more slowly. They should drift away into the vast emptiness by their own momentum. Yet when we measure their speed, we find they are orbiting just as fast as the stars near the center. It is as if the entire galaxy is embedded within a massive, unseen sphere of matter, its immense gravity holding the entire structure together, keeping everything in place. This unseen sphere provides the gravitational anchor that visible matter clings to, a hidden component that makes up the vast majority of a galaxy's total mass. Without this dark framework, the beautiful, ordered spirals we see would simply not exist. They would fade into disorder, their stars spread across an empty sky. So the next time you gaze at a photograph of a distant galaxy, remember you are only seeing the glittering decoration on the surface of a much deeper and far more massive hidden reality. This hidden framework of dark matter provides the gravitational anchor, but it cannot create motion on its own. For that, we need to introduce the third principle, the cosmic force of spin. Why do galaxies spin at all? The answer is written in the fundamental laws of physics, in a concept known as the conservation of angular momentum. You have witnessed this principle in action yourself, perhaps without even realizing it. Watch a figure skater begin a slow spin with their arms outstretched. As they pull their arms inward, their body responds by spinning faster and faster. They are not adding new energy, they are simply conserving the momentum they already had, concentrating it into a smaller space, which results in a dramatic increase in their rotational speed. The early universe performed this exact same trick, but on a scale so grand it is almost impossible to picture. In the beginning, the vast, formless clouds of primordial gas had tiny, almost imperceptible motions. They were not perfectly still. They drifted and shifted with faint, swirling tendencies, subtle movements inherited from the earliest moments of the cosmos itself. As gravity began its patient work, drawing this enormous cloud inward, it encouraged the gas to gather into a much smaller, denser volume. Just like the skater pulling in their arms, this gathering had a profound effect. The cloud's initial, faint whisper of rotation was amplified. That tiny, original drift became a powerful, coherent spin. This is the transformative power of conservation. What was once a slow, vast, and wandering drift became the organized, majestic rotation that defines a spiral galaxy. This principle of spin is what gives a galaxy its dynamic form. Without it, the gathering cloud of gas might have simply formed a giant, featureless sphere of stars. But with spin, the cloud could not gather equally in all directions. The centrifugal force of its rotation pushed outward, resisting gravity's pull along the equator, while gravity continued to draw with full force from the poles. The result was a natural and inevitable flattening, the formation of a thin, rotating disk. This is the final, breathtaking transformation from a wandering cloud into an ordered, spinning island of stars. This spin is not just a decorative feature, it is a crucial dimension of the cosmic architecture, a fundamental property that guides how a galaxy evolves, how stars are born within its spiral arms, and how it interacts with its neighbors. The universe took a faint initial wobble and, through the patient application of physical law, turned it into a whirlpool of creation. This grand dance of gravity, dark matter, and spin does not happen in isolation. The true masterpiece reveals itself only when we pull our perspective back, far beyond the boundaries of any single galaxy. From this cosmic vantage point, the universe resolves into a structure of breathtaking scale and elegance, the cosmic web. Picture the universe not as a random scattering of stellar islands, but as a single, interconnected network, a tapestry woven from threads of galaxies. These threads, called filaments, stretch across the unimaginable emptiness for hundreds of millions of light years. They curve and intersect at dense nodes, where thousands of galaxies swarm together in massive clusters. And between these brilliant threads lie the voids, unimaginably vast regions of near-total emptiness, cosmic deserts that make up most of the volume of the observable universe. This is the large-scale structure of everything, the ultimate expression of the hidden architecture. To grasp its form, you might think of the intricate network of neurons in a human brain, a complex web of connections transmitting signals across a vast, dark space. Or on a more everyday scale, imagine the delicate foam on a cappuccino, with its interconnected bubbles and empty pockets. The cosmic web is the universe's version of this foam, with galaxies tracing out the soapy walls and the voids forming the empty interiors. This pattern was not sculpted by chance. Its blueprint was imprinted onto the cosmos in the very first moments of existence, from the microscopic quantum fluctuations of the Big Bang. These tiny wrinkles in the fabric of spacetime were the seeds, the initial conditions. Over billions of years, gravity acted as the master builder, patiently amplifying those seeds, pulling matter into the dense filaments and nodes and emptying out the voids. The web you see today in all its glory is the final, grown-up version of that infant pattern. It shows us that the hidden order we find within a single spiral galaxy is merely a local expression of a universal principle. The architecture is not just in the galaxies themselves, but in the very arrangement of space, a fundamental geometry written into the cosmos. So when you look at a map of the cosmic web, you are not just looking at where things are. You are looking at the preserved echo of the universe's first instant, a memory from the dawn of time, expanded to a scale that defies human comprehension. That faint, ancient whisper you just heard of, the one that imprinted the cosmic web, has a name and a face. We can actually see it. The oldest light in the universe still washes over us, a fossil glow from a time when the cosmos was a mere infant. This is the cosmic microwave background, and it holds the ultimate secret. When we map this radiation with incredible precision, we find it is not perfectly uniform. It is painted with the faintest of spots, regions that are just a few thousandths of a degree warmer or cooler than their surroundings. These tiny temperature differences are not random noise. They are a cosmic treasure map. Each slightly warmer patch marks a region where the early universe was just a little bit denser, a little more crowded with matter and energy. Each cooler spot signifies a place that was ever so slightly more empty. These are the primordial density fluctuations, the quantum ripples from the Big Bang itself. To understand their scale, think of a perfectly smooth pond. Now imagine tossing a single handful of fine sand into its center. The ripples that spread out are tiny, almost imperceptible. But if you could instantly stretch that entire pond to the size of an ocean, those same ripples would become vast, rolling swells, defining the entire surface. This is precisely what a period of hyper-expansion called inflation did to our universe. It stretched those initial microscopic quantum jitters, those faint ripples in the fabric of reality, to proportions of astronomical scale. They became the grand, underlying pattern for everything. This is the hidden blueprint. The slightly denser regions became the future filaments and nodes of the cosmic web, the great gathering places for galaxies. The slightly emptier regions evolved into the cosmic voids. The pattern we see in the ancient light is the genetic code for all the structure we find in the universe today. Your very existence, the planet you live on, the star that gives you light, and the galaxy that star calls home, all trace their ultimate origin back to one of those specific, slightly warmer spots on that ancient map. The universe was not born blank. It was born with a subtle texture, a predisposition for order, and we are the legacy of that first, delicate imprint. Yet this grand cosmic blueprint is not a static sculpture. The galaxy it builds is a dynamic and ever-changing ecosystem. For a galaxy to achieve its mature form, a crucial fifth principle must enter the stage, a process of powerful creation and transformation. The most massive stars are the primary agents of this change. They burn through their nuclear fuel in a cosmic blink, living lives of intense but brief brilliance. Their final acts are monumental. They conclude their existence in spectacular supernova events, releases of energy so vast they can briefly outshine an entire galaxy. But their purpose is not merely conclusion. In these profound transitions, these stars forge the heavy elements essential for life itself, everything from the oxygen we breathe to the iron in our blood, and scatter them out across the galaxy. At the same time, throughout their short lives, these titans shape their surroundings with powerful stellar winds, steady streams of charged particles that push and energize the surrounding gas. Together, supernova and stellar winds act as a galactic thermostat. This is the principle of feedback. When star formation runs too hot, creating too many of these massive stars too quickly, their combined winds and eventual energetic releases heat the galactic gas, making it too turbulent to collapse easily and form new stars. This effectively turns down the thermostat, slowing the rate of star birth. It is a self-regulating cycle. Without this powerful feedback, a galaxy might consume all its gas in a single, frantic burst of star formation, leaving behind an inert and unchanging system. Instead, the cycle of stellar existence ensures that star formation is a long, sustainable process, and that the galaxy is progressively enriched with the chemical building blocks for planets and, ultimately, life. This dynamic interplay is what sculpts a galaxy's final character, carving out its structure and writing its chemical history. The immense energy of a supernova is not an agent of randomness, but an essential craftsman in the hidden architecture, ensuring the galaxy evolves with both power and grace. Edwin Hubble gave the cosmos a filing system. By carefully observing the shapes of distant galaxies, he arranged them into a simple but powerful diagram that looks like a giant tuning fork. On one prong, you find the elegant spiral galaxies, from those with tight, wound-up arms to those with loose, open structures. On the other prong sit the barred spirals, galaxies with a distinct straight bar of stars cutting through their center. And at the base of the fork are the elliptical galaxies, smooth, featureless spheres or ovals of stars that glow with a soft, golden light. This was more than just celestial stamp collecting. This Hubble sequence is a field guide to the life stories of galaxies. The shape of a galaxy is a direct record of its past. A majestic, undisturbed spiral speaks of a quiet, isolated existence, with gas settling into a stable, rotating disk where new stars can form in an orderly fashion. Its pinwheel arms are not solid structures but dynamic waves of density, like traffic jams on a cosmic highway, triggering the birth of brilliant new stars. In stark contrast, a giant elliptical galaxy, a vast and shapeless swarm of ancient stars, tells a much more intense tale. Its random orbits and lack of gas suggest a history of galactic mergers, colossal encounters where spiral galaxies came together, their orderly disks transformed into a chaotic, simmering ball of stars. The tuning fork, therefore, is not just a static gallery of types. It is a snapshot of an evolutionary journey. A spiral galaxy can be reshaped into an elliptical through a dramatic merger, its history rewritten in a single, powerful chapter. But modern astronomy has pushed us far beyond Hubble's elegant diagram. We now know of ultra-diffuse galaxies, ghostly collections of stars so faint they are almost invisible, challenging our ideas of how galaxies hold themselves together. We find ring galaxies, perfect circles of stellar light that form when one galaxy passes through the heart of another, a cosmic bull's-eye revealing the dynamics of interstellar interactions. And then there are the peculiar galaxies, the oddballs that defy any simple classification, their twisted and disturbed shapes whispering of recent gravitational encounters and near misses. The universe, it turns out, is a workshop of infinite architectural variety. The Hubble sequence was our first key to understanding the basic blueprints, but the full catalogue of cosmic design is a living document, forever being updated with every new and wondrous discovery. A spiral galaxy is a cosmic engine of perfect equilibrium. Its graceful, arching arms and brilliant core represent a state of balance achieved over billions of years, a dynamic stability between the relentless pull of gravity and the outward push of centrifugal force. That majestic pinwheel shape is no accident. It is the signature of a system in harmonious motion, where every star follows its own orbital path while contributing to the whole. At the heart of this order lies a beautiful paradox. Those iconic spiral arms, which seem so solid and permanent, are actually illusions of structure. They are not fixed streams of stars like cars on a racetrack. Instead, they are density waves, moving patterns of compression that travel through the galactic disk, much like a traffic jam moves along a busy highway. Individual cars enter the jam, slow down for a time, and then eventually speed up and exit, while the jam itself persists. In a galaxy, stars and vast clouds of gas enter the spiral arm region, experience a gravitational squeeze within this cosmic traffic jam, and then slowly drift out the other side. It is this compression that triggers one of the universe's most magnificent processes. As the giant clouds of gas are forced together within the wave, they collapse under their own gravity, igniting the birth of brilliant new stars. The spiral arms we so admire are actually stellar nurseries, glowing with the intense light of these young, hot stars. This is why the arms appear so bright and defined. They are not defined by the stars themselves, but by the ongoing, vibrant process of creation happening within them. The entire galaxy is a self-perpetuating cycle. The density wave shapes the star formation, and the energy from those new stars, in turn, helps to maintain the wave itself. This elegant dance ensures the spiral galaxy remains a living, evolving entity, a testament to how transient patterns can give rise to enduring beauty. But not every galaxy is a graceful, spinning disk. Some are the silent giants of the cosmos, the elliptical galaxies. Picture a vast, glowing sphere of ancient stars shining with a soft, golden light. It has no spiral arms, no dust lanes, no obvious structure. It is simply a colossal, smooth swarm of stars, a celestial city whose inhabitants all move on random, meandering paths. This is not a galaxy of birth, but one of maturity, the final form after a profound and dramatic history. These immense structures are the direct result of galactic mergers, the slow, cosmic dance of entire spiral galaxies meeting and combining. When two spirals come together, their gravitational embrace is so powerful that it completely reshapes the orderly orbits of billions of stars. The beautiful, flat disk is transformed, its original structure set aside, and the stars are gathered into a three-dimensional cloud, a simmering ball of stellar light. The vast reservoirs of gas that fuel star formation in spirals are either used in a final, brilliant burst of new stars or dispersed far from the galaxy. This leaves the elliptical galaxy with a population of old, red stars with little material left to create new ones. It is a quiet, settled place, yet this apparent randomness is not disorder. It is a different kind of order, a relaxed and stable equilibrium achieved after a period of immense change. The galaxy has been fundamentally reshaped, its architecture transformed from a dynamic disk into a serene, spherical swarm. These silent giants teach us that the universe has more than one way to build a galaxy, and that even from the most energetic of encounters, a new and majestic form of stability can arise. Yet for every majestic spiral and serene elliptical, there exists a cosmic rebel. These are the irregular galaxies, the rule breakers of the universe that refuse to conform to any simple shape. Often small and seemingly unstructured, they look like splatters of stellar paint across the dark canvas of space. Their forms are wonderfully chaotic, lacking the defined centers or symmetrical arms of their more ordered cousins. But this apparent randomness is not a failure of design. It is a different kind of architectural principle, one driven by raw, creative energy. Look no further than our own galactic neighbor, the Large Magellanic Cloud. It appears as a vast, glowing cloud of scattered light, a place where stars are born in brilliant, energetic clusters. This intense and vibrant star formation is the hallmark of the irregular galaxy. Without a dominant central structure or a stable rotational spin to impose order, the gas within these galaxies remains in a constant state of motion. This motion becomes a catalyst. Giant clouds of gas come together and collapse with incredible frequency, igniting waves of new stars in a spectacular display of cosmic fertility. The very forces that create this irregularity, this lack of a grand design, are the same forces that make them stellar nurseries of immense power. Their dynamic appearance is a direct result of their rich history. Many irregular galaxies are shaped by gravitational interactions, their forms influenced and reshaped by the tidal forces of a larger galactic neighbor. This gravitational dance stirs up their internal gas, preventing it from settling into a calm, orderly disk and instead fueling a firestorm of creation. So while they may lack the graceful symmetry of a spiral, they possess a vibrant, untamed beauty all their own. They teach us a profound lesson about the cosmos. Chaos is not the absence of order. It is a different kind of order altogether, a creative and energetic state that is just as essential for building a complete picture of the universe. In the grand architectural blueprint, these galaxies are the workshops where the most fundamental process of all, the birth of stars, occurs with breathtaking intensity. The graceful spin of a galaxy holds a secret that would unravel our most basic assumptions. If you were to watch our own Milky Way from a distance, you would expect to see a very specific kind of motion. The stars close to the bright, dense center where gravity's pull is strongest should be whipping around at tremendous speeds, but as you look further out toward the sparse outer edges of the spiral arms, those distant stars should be moving much more slowly, drifting along in a leisurely orbit. This is the simple logic of our solar system, where distant Pluto crawls in its path while Mercury races around the Sun. For decades, astronomers applied this same logic to entire galaxies, confident that the familiar rules of gravity would hold. Then they actually measured the speeds. The results were not just surprising, they were impossible. Stars at the very fringe of a spiral galaxy, far from the central glow, were not moving slowly at all. They were orbiting just as fast as the stars near the center. The rotation curve, the graph that plots orbital speed against distance from the center, did not fall away as predicted. It stayed flat. This was a profound contradiction, a cosmic anomaly that shook the foundations of physics. If the visible matter was all there was, these outer stars should have been flung off into the void long ago, their velocity overcoming the weak gravitational grip of the distant core. The only logical conclusion was that there had to be more, much more, than what our telescopes could capture. The galaxy had to be embedded within an enormous, massive sphere of something unseen. a dark matter halo whose immense gravity was anchoring these speeding stars, creating the flat rotation curve we observe. This hidden mass does not concentrate in the bright disk. It forms a vast spherical cloud that envelops the entire luminous galaxy, its gravitational influence reaching far beyond the last visible star. That simple, flat line on a graph became one of the most powerful clues in the history of science, forcing us to accept that the universe is built from a substance we cannot see, a hidden architecture that holds the light together. But what holds the delicate veins of a galaxy together, beyond the crushing pull of gravity and the anchoring presence of dark matter, another invisible architect is at work. Stretching between the stars, woven through the vast clouds of gas and dust, are immense magnetic fields. You cannot see them, and their individual strength is almost negligible, yet together they form a pervasive framework for the entire galaxy. To understand their subtle power, picture a vast, invisible network of fibers running through a cloud of glitter. The glitter represents the stars and gas, while the fibers are the magnetic field lines. The glitter can move, but its motion is gently guided and shaped by the unseen structure surrounding it. This is the role of magnetism in the interstellar medium, the space between the stars. These fields channel the flow of gas, steering it along invisible pathways and helping to shape the great clouds where new stars are born. They can prevent a cloud from collapsing too quickly, or help to squeeze a region just enough to trigger the ignition of a new sun. They even act as cosmic accelerators, whipping charged particles to nearly the speed of light, creating the mysterious cosmic rays that constantly rain upon our world. How can we possibly detect something so intangible? Astronomers use a clever trick of physics. When starlight passes through a region with a magnetic field, the dust grains in that region align themselves with the field like tiny compass needles. This alignment polarizes the light, meaning the light waves vibrate in a preferred direction. By carefully measuring this subtle polarization in the light we receive, we can effectively map the invisible magnetic fields of distant galaxies. This reveals a breathtaking reality. The hidden order of a galaxy is not solely a matter of gravity and mass. It is also electromagnetic. This delicate, invisible framework adds a final layer of complexity to the cosmic architecture, proving that the universe builds its greatest structures using every tool at its disposal, from the most dominant forces to the most subtle and pervasive fields. Galaxies are not the isolated islands they appear to be. They are social creatures, bound together by gravity in a slow, cosmic dance that can last for billions of years. In the grand timeline of the universe, galactic interactions are not rare accidents, but a fundamental part of how the cosmos builds its largest structures. This process, known as galactic merging, is a story of transformation on a scale that defies human comprehension. When two spiral galaxies are drawn together, their initial approach is almost stately. They do not meet in a single, fiery instant. Instead, they begin a long, graceful pas de deux, swinging past each other in a gravitational embrace that slowly tightens over countless orbits. During these close passes, their mutual gravity acts as a sculptor of unimaginable power. It pulls vast streams of stars and gas from their familiar paths, stretching them out into long, luminous tidal tails that can arc across hundreds of thousands of light years. These brilliant bridges are the first visible sign of the profound transformation underway. Inside the galaxies, the orderly rotation of the disks is gently reshaped. The calm, circular orbits of billions of stars are stirred into a new, three-dimensional swarm. It is this fundamental reshaping of stellar motion that forges a new kind of galaxy. The two distinct spiral disks with their flat, ordered structures are gradually blended, their individual forms giving way to create a single, vast, and smooth ball of stars. This is the birth of a giant elliptical galaxy. Yet within this apparent disorder lies an immense creative force. As the vast clouds of gas within the two galaxies are gently pressed together during the encounter, they ignite in a wave of new star birth. This is known as a starburst, a period where the galaxy can form stars hundreds of times faster than our quiet Milky Way. For a brief, brilliant period, the merging galaxy becomes one of the brightest objects in the universe, a beacon of creation born from connection. The entire process is a stunning demonstration of cosmic renewal. The energy of the merger is not an end, but a catalyst. It reshapes old forms to create new, more massive structures, and in doing so, it seeds the future with the heavy elements forged in its stellar furnaces. The serene elliptical galaxies we see today are the quiet, mature results of these ancient, energetic, and profoundly creative encounters. Deep within the heart of our galaxy, and nearly every other large one, lies a gravitational titan. This is the supermassive black hole, an object so dense that its pull not even light can escape. But to call it a simple cosmic vacuum cleaner is to misunderstand its profound role. These black holes are the quiet, beating hearts of their galactic cities, their immense presence subtly guiding the rhythm of life across billions of stars. The most astonishing clue to their importance is a mysterious correlation, a cosmic rule that links the invisible to the visible. The mass of a galaxy's central bulge of stars, that bright central hub, is directly proportional to the mass of its supermassive black hole. A larger galactic core means a more massive black hole. This is not a coincidence. It is a signature of a deep, fundamental relationship, a conversation between the growth of a galaxy and the growth of the giant at its center. They evolved together, their fates intertwined across cosmic time. How can something that lives in such profound isolation exert influence over an entire galaxy? The answer lies in its occasional, spectacular awakenings, when vast amounts of gas and dust spiral inward, drawn toward the event horizon. This material doesn't just vanish quietly. It forms a searingly hot, rapidly spinning disk of matter, an accretion disk that glows with the light of billions of stars. In this active state, the galaxy's core becomes an active galactic nucleus, a beacon of unimaginable power. But this engine does more than just shine. It can send out colossal jets of energy and matter, moving at nearly the speed of light, that reach far out into the galactic halo. This is where the black hole reveals its true nature as a galactic regulator. These tremendous outpourings release energy into the galaxy's vast reservoirs of star-forming gas. They heat it, they stir it, they push it away. This process, a form of black hole feedback, acts as a cosmic thermostat for star formation. If too many stars begin to form, sending too much gas toward the center, the black hole can awaken and release a wind that clears the gas away, effectively turning down the star-making furnace. This prevents the galaxy from consuming its fuel in a single, brief burst, ensuring a long and stable evolution. The supermassive black hole is not a destroyer. It is a balancing force, a hidden governor whose immense gravity and occasional activity are woven into the very architecture of the galaxy, maintaining the delicate equilibrium that allows for a rich and lasting cosmic story. The address of a galaxy within the cosmos writes its entire life story. Venture into the heart of a galaxy cluster, a metropolis of thousands of galaxies bound together by gravity, and you will find a world of intense interaction. Here, galaxies are not serene islands. They are neighbors in a dense cosmic city, constantly brushing past one another in a slow gravitational dance. This environment is full of activity. As a galaxy moves through the crowded cluster, it plows through a superheated, thin gas that fills the space between galaxies. This intergalactic medium acts like a powerful wind, steadily clearing the galaxy of its own cold gas, the very raw material needed to form new stars. This process, called ram pressure stripping, leaves the galaxy with less fuel. Without fresh resources, star formation gradually slows. the galaxy's vibrant blue star-forming regions grow quiet, leaving behind a population of aging red stars. This is why the cores of dense clusters are often home to these red and quiet galaxies, their era of brilliant creation now part of their history. Their structure has been deeply influenced by their location. Contrast this with a galaxy living in the cosmic countryside, what astronomers call the field. An isolated field galaxy, like our own Milky Way, exists in a much quieter neighborhood. It is free from the constant gravitational nudges and the sweeping winds of a dense cluster. Here, it can hold onto its vast reservoirs of gas, allowing it to continue forming new stars at a gentle pace for billions of years. Its spiral arms glow with the blue light of young stellar nurseries, a sign of its peaceful and resource-rich existence. Then there are the galaxies that reside in the most solitary places of all, the cosmic voids. These are the universe's great open spaces, regions hundreds of millions of light years across that are almost entirely empty. A void galaxy is an isolated island in an ocean of stillness. It is so alone that its evolution is guided almost entirely by its own internal processes, untouched by the outside world. The grand pattern of the cosmic web, with its dense clusters and vast empty voids, is not just a map of where things are. It is a blueprint for how things become. The hidden architecture of a single galaxy is not merely an internal affair. It is a dialogue, a constant conversation between the forces within and the immense, shaping presence of the environment without. To witness the universe's first architectural sketches, we must journey back across unimaginable eons. The James Webb Space Telescope acts as our time machine, its powerful gaze fixed on a seemingly empty patch of sky known as the deep field. What appears to our eyes as vacant darkness is, to this incredible instrument, a window to the dawn of time. It reveals the faint, ghostly forms of the very first galaxies, structures that ignited when the cosmos was a mere infant, just a few 100 million years old. These are not the majestic, well-defined spirals and ellipticals we see today. They are the cosmic equivalent of foundational blocks, small, clumpy, and intensely energetic. They lack the clear, organized rotation of mature galaxies, appearing instead as brilliant knots of newborn stars, shining with a raw, blue light. Their shapes are irregular and chaotic, like droplets of water splattered across a surface, each one a frantic nursery of stellar birth. Why do they look so different from our own Milky Way? The answer lies in their youth and their pristine environment. These infant galaxies were forming from gas that had never been touched by the earlier cycles of stellar existence. It was pure hydrogen and helium, without the heavy elements that later generations of stars would produce. This pure gas behaved differently, collapsing into stars with a wild, untamed fervor. They were also much smaller than the giants we see today, the building blocks that would later merge and assemble through countless encounters to create the grand galactic structures we recognize. Observing them is like looking at the foundation of a great city before the first bricks are even laid. You can see the initial outlines, the first gatherings of material, the very first strokes of order being drawn onto a blank and formless canvas. This is the hidden architecture in its most raw and primordial state, a blueprint written in fire and light at the beginning of everything. These infant galaxies were the raw material, but how can we possibly test our theories of their growth? We build our own universes. Inside the world's most powerful supercomputers, entire cosmos are born from lines of code. These are cosmological simulations, vast digital laboratories where scientists can replay the entire history of the universe, watching its grand architecture assemble itself from the first moment to the present day. Projects with names like IllustrisTNG and Eagle begin with the fundamental recipe of the cosmos. They start with the initial conditions of the Big Bang, a nearly uniform sea of dark matter and primordial gas, seeded with those tiny quantum ripples we detected in the ancient light. Then they press start. The simulation unleashes the complete set of physical laws, the mathematics of gravity, fluid dynamics, and magnetic fields, and lets it all run forward across billions of virtual years. You can watch it happen. At first, the dark matter, responding only to gravity, begins to clump into a vast cosmic web of filaments and halos. This invisible scaffold emerges first, just as our theories predicted. Then ordinary gas, the baryonic matter, feels the pull of this dark framework and begins to flow into the densest knots. It spins, it cools, and it collapses to form the first virtual stars and galaxies. You witness mergers as small blobs of light swirl together to build majestic spirals and giant ellipticals. You see stellar explosions scatter newly forged heavy elements back into the virtual gas, enriching the next generation of stars. This is more than a movie. It is a dynamic test of our deepest understanding. What makes these simulations truly revolutionary is their predictive power. When astronomers look into these digital universes, they find galaxies that look and behave almost exactly like the real ones we observe through our telescopes. The simulated galaxies have the right sizes, the correct masses, and they fall neatly along Hubble's tuning fork. They even show the same strange anomalies, like the flat rotation curves that first hinted at dark matter. This remarkable agreement between the digital and the real is a powerful vote of confidence, telling us that our models of physics, though incomplete, are on the right track. But the simulations do more than just confirm what we already know. They reveal the hidden conversations between the different forces at play. They show us how a supermassive black hole's outburst can regulate star formation across an entire galaxy, or how the gentle pressure of intergalactic wind can strip a galaxy of its star-forming fuel. These are processes that unfold over timescales far too long for us to ever observe directly. Yet in the universe in a box, we can watch them happen in a matter of days. These digital realms are our ultimate tools for discovery, allowing us to experiment with the cosmos itself, to tweak the laws of physics and ask the most profound what-if questions, all from within a supercomputer's memory. The universe remembers its own first sounds. Etched into the vast cosmic web in the very spacing of galaxies is a subtle, repeating pattern known as Baryon acoustic oscillations. This is the preserved imprint of a primordial rhythm, a pressure wave that once rippled through the newborn cosmos. In its earliest moments, the universe was a searingly hot, dense soup of particles and light, a plasma so thick that photons could not travel freely. Within this churning medium, gravity was already at work, trying to pull matter into denser clumps. But this inward pull was met with a powerful outward force, the intense pressure of the trapped radiation. This conflict created an oscillation, a single, massive sound wave that surged outward from every slightly denser region. For nearly 400,000 years, this wave expanded through the plasma at a significant fraction of the speed of light, pushing a shell of matter ahead of it like a cosmic snowplow. Then the universe cooled just enough for a monumental change. Atoms formed, and light was suddenly set free in what we observe as the cosmic microwave background. The wave froze in its tracks. In that instant, the traveling sound wave was imprinted onto the cosmos, leaving behind a spherical shell of matter with a very specific radius. This is the standard ruler. We see its signature today as a subtle statistical preference for galaxies to be separated by a certain distance, a distance that corresponds to that frozen sound wave's reach. By measuring this preferred scale in the galaxy distribution around us, astronomers have a fixed measuring stick. They can compare the apparent size of this ruler at different distances, and thus at different epochs in cosmic history, to see how the fabric of space itself has stretched over billions of years. The Baryon acoustic oscillation is more than a preserved echo. It is a direct message from the first moments, a constant, quiet hum underlying all of cosmic architecture that allows us to map the expansion of everything with remarkable precision. This cosmic map reveals an even grander motion, a river of galaxies flowing through the void. Our entire local group, including the Milky Way and Andromeda, is not merely expanding with the universe. We are caught in a vast, silent current, drawn toward a specific point in the darkness behind the constellation Centaurus. Astronomers call this mysterious gravitational focal point the Great Attractor. Its discovery emerged not from seeing a brilliant object, but from listening to the subtle motions of the galaxies around us. By carefully measuring the cosmic microwave background, the afterglow of the Big Bang, we have a fixed reference frame, a stationary background against which we can gauge our own peculiar velocity. The data revealed an astounding truth. Our galactic neighborhood is moving at an incredible speed of over 600 kilometers per second, all of it directed toward this unseen concentration of mass. This is not a gentle drift but a powerful, directed flow, as if some immense, hidden presence were gently guiding our corner of the universe. The source of this immense pull remains partially obscured, hidden behind the dense star fields and dust of our own galaxy's central plane, a region astronomers poetically call the zone of avoidance. But what could possibly exert such a gravitational influence? The Great Attractor is not a single, monstrous object. It is a gravitational focal point, the center of mass for an enormous confluence of matter. We now understand it to be the heart of the Laniakea supercluster, a vast filament of over 100,000 galaxies to which our Milky Way belongs. This supercluster is like a continent in the cosmic web, and the Great Attractor is its most densely populated capital city, a massive node where several galactic filaments intersect. The pull we feel is the combined gravity of this entire immense structure, a concentration of both visible galaxies and, more importantly, their accompanying dark matter halos. This discovery fundamentally changed our perspective on cosmic architecture. It shows us that the hidden framework is not static. It is dynamic, flowing, and alive with motion on the grandest scales. Entire clusters of galaxies move in concert, like leaves caught in a gentle but immense river current, all guided by the invisible topography of mass woven into the fabric of the cosmos. The quest to fully map and comprehend these flows continues, a humbling reminder that we are but a small part of a much larger and still mysterious gravitational landscape. Our own galactic home is on an unstoppable collision course. The familiar spiral of the Milky Way, which has spun in quiet isolation for most of cosmic history, has a destiny written in gravity. It is slowly, inevitably falling toward its colossal neighbor, the Andromeda Galaxy. This is not a future of random chance, but a direct consequence of the hidden architecture we have been exploring, a gravitational bond that has sealed our fates for billions of years. The forecast for this event is one of the most certain in all of astronomy. We know it is coming because we can measure the subtle blue shift in Andromeda's light, a telltale sign that it is moving toward us, not away. We can calculate its trajectory with precision. This is not a guess, it is a cosmic clock that has been ticking down since before our planet even formed. The two great spirals are currently separated by about 2.5 million light-years, but that gap is closing at a rate of over 100 kilometers every single second. The dance has already begun. The first close pass will not happen for another 4 billion years. When it occurs, it will be a slow-motion performance of unimaginable scale. The galaxies will not crash directly into one another like two cars. Instead, they will swing past each other in a gravitational embrace that will fundamentally reshape them both. From our perspective, should any observers be here to see it, the night sky would transform into a spectacle beyond comprehension. The Andromeda Galaxy, currently a faint smudge of light, would grow to dominate the heavens, its spiral arms stretching across the entire celestial dome. As the galaxies make their first pass, their mutual gravity will act as a sculptor. It will pull long, luminous streams of stars from their outer edges, creating brilliant tidal tails that arc across the darkness like celestial brushstrokes. The orderly rotation of both disks will be disrupted, their beautiful spiral patterns stretched and warped beyond recognition. This initial encounter will be followed by a slower, drawn-out period of separation and return. Over the next 1 to 2 billion years, the two altered galaxies will swing away, only to be pulled back together by their unbreakable gravitational tether. They will fall toward each other again and again, each pass stirring their stellar populations more thoroughly, like two great clouds of glitter being gently mixed together. The final merger will be a drawn-out, beautiful chaos. The distinct identities of the Milky Way and Andromeda will be lost, their stars and dark matter halos blending into a single, new structure. The vast clouds of gas within both galaxies will interact, triggering a brilliant but final burst of new star formation, a last blaze of stellar birth before the long quiet. The final product of this multi-billion-year process will not be a spiral galaxy. The elegant disks will be gone, their ordered motion transformed into a random, three-dimensional swarm. The result will be a new, larger type of galaxy, a giant elliptical. It will be a smooth, featureless sphere of ancient stars, a serene and quiet testament to a dramatic past. This cosmic forecast shows us that the patterns we see today are not permanent. The hidden architecture is a dynamic, ever-changing blueprint. The spiral galaxy we call home is just one chapter in a much longer story, a story of construction and transformation that is still being written across the deep time of the universe. Yet for every question we answer, a deeper mystery comes into view. We have mapped the hidden architecture of galaxies, but we still do not know what the primary building material actually is. Dark matter remains the ghost in the cosmic machine, a substance that interacts with our world only through gravity. We know it is there, we can trace its gravitational shadow, but its fundamental nature is one of the greatest puzzles in modern physics. Is it a sea of exotic, undiscovered particles, trillions of which might be passing through you at this very moment without any effect? Or does its mystery require us to rewrite the very laws of gravity themselves? We simply do not know, and then there is dark energy, an even more perplexing presence. This is not a pulling force like gravity, but a pushing force, a repulsive energy inherent to the fabric of space itself. It is the engine driving the accelerating expansion of the universe, causing galaxies to rush away from one another at ever-increasing speeds. We can measure its effect, but we have no idea what it is. Think of it as the ultimate cosmic anti-gravity, a pressure from the vacuum of empty space that is slowly stretching the very cosmos apart. These two unknown components, dark matter and dark energy, together make up 95% of the entire universe. Everything we see and know, every galaxy, every star, every planet, constitutes a mere 5% of the cosmic whole. We are like explorers who have beautifully mapped the coastlines of a continent, but have only just begun to guess at the vast, uncharted interior that lies beyond. The connection between the infinitely small and the infinitely large presents another profound frontier. How do the fleeting, random jitters of the quantum world, the fundamental uncertainty at the heart of every particle, become the grand, structured filaments of the cosmic web? How does a fluctuation smaller than an atom dictate the future location of a galaxy cluster a billion light-years across? Our current physics has two sets of rules, one for the very small and one for the very large, and they do not yet fit together into a single, coherent picture. A theory of quantum gravity, a way to describe the force that shapes the cosmos using the language of the tiny, remains the great goal of theoretical physics. These are not failures of our science, they are the very signs of a living, breathing field of discovery. an unanswered question is not a wall but a doorway. It is an invitation for the next generation of telescopes, the next revolutionary experiment, the next brilliant mind to look at the data and see a pattern no one else noticed. The map of cosmic architecture is not finished. In fact, we have only just begun to sketch its most basic outlines, and its most fundamental secrets are still waiting, hidden in the darkness, for their moment to be revealed. This cosmic dance between chaos and structure reaches far beyond the equations on a page. It touches something fundamental within us, a deep-seated human need to find meaning in the patterns we observe. For centuries, we looked at the starry sky and saw either a perfect, divine clockwork or a beautiful, meaningless accident. Modern cosmology presents us with a third, more nuanced possibility. The universe is not a perfect machine, nor is it pure randomness. It is a system with an inherent tendency to build complex, stable structures from simple, initial conditions. The quantum ripples of the Big Bang were random, but the laws of physics that amplified them are not. They are the universal constants, the fixed rules of engagement that patiently guide chaos toward cosmos. This is not a predetermined design, but a predisposition for order. It is as if the universe was given a set of simple, elegant tools, and with those tools alone, it built galaxies, stars, planets, and life. So where does that leave us? We are not mere accidents in a cold, indifferent void, nor are we the central purpose of a meticulously planned creation. We are something perhaps more remarkable. We are a natural expression of a universe that has the capacity to organize itself, to build complexity, and to eventually become aware of its own existence. We are the universe in a very real sense beginning to understand itself. The spiral arm of a galaxy and the double helix of our own DNA are both expressions of the same underlying principle, that nature finds efficient, stable, and beautiful forms. This scientific journey does not diminish our sense of wonder, it grounds it in a profound new reality. The awe we feel when we look at a Hubble image of a distant galaxy is not just an aesthetic reaction. It is a recognition of a shared heritage. We are made of stardust, yes, but we are also built upon the same architectural principles that sculpted those stars. Our search for meaning and our exploration of the cosmos are not separate endeavors. They are two sides of the same coin, the human mind reaching out to comprehend the very processes that gave it form. In uncovering the hidden architecture of the galaxies, we are not just mapping the heavens. We are reading our own cosmic story and discovering that our deepest questions about existence are woven into the fabric of everything. This quest for cosmic architecture is far more than an academic exercise. You might naturally ask what any of this has to do with the world you walk through every day. The answer is woven into the very fabric of our modern existence. The drive to see farther and understand more about the universe relentlessly pushes the limits of our technology. Consider the digital camera in your phone. Its core technology, the charge-coupled device, was perfected by astronomers striving to capture the faint light of distant galaxies. That same technology now powers medical imaging systems, allowing doctors to see inside the human body with stunning clarity to diagnose illness early. Or think of the internet, a global network for sharing information. The very software used to manage the immense data flow from radio telescopes helped pave the way for the World Wide Web. These are not happy accidents. They are direct results of our need to solve the profound puzzles of the cosmos, innovations born from our desire to map the great unknown. But the value runs even deeper than practical invention. This exploration speaks to a fundamental human need, a curiosity etched into our spirit. We are storytellers by nature, and the grandest story of all is the one of our own origins. Knowing that the iron in your blood was forged in the heart of an ancient star, or that the spiral of a galaxy shares a mathematical kinship with the pattern of a seashell, changes your relationship with reality. It offers a profound sense of perspective. Your daily worries, while entirely real, are set against a backdrop of almost unimaginable scale and beauty. This perspective is not meant to diminish our lives, but to enrich them with a deep and humbling awe. It reminds us that we are not just living in the universe, we are a way for the universe to know itself. And that is a connection that matters to every single one of us. We began by gazing into what seemed like a beautiful, chaotic scattering of stars, a canvas of infinite complexity. Our journey has taken us deep into the heart of that mystery, revealing a cosmos brimming with hidden architecture. We discovered the invisible hand of dark matter, the quiet scaffold that holds galaxies together. We traced the grand design of the cosmic web back to its origin in the faint, preserved ripples from the dawn of time itself. We learned that galaxies are not static islands, but dynamic, evolving entities, shaped by fundamental forces and transformed by immense interactions over billions of years. The spirals, the ellipticals, the irregular rebels, each tells a story of gravity, spin, and cosmic history. The patterns within the infinite chaos reveal a universe of breathtaking order and profound beauty. This new perspective transforms the night sky. It is no longer a random splash of light, but a glimpse into a grand, hidden design, a decipherable map of cosmic structure. Let this understanding inspire your own sense of wonder. The next time you stand beneath a clear, dark sky, look up, see the stars not as isolated points, but as part of a vast, interconnected tapestry, a living narrative written in gravity and light. We would love to hear which cosmic pattern amazed you the most. Was it the quiet pull of dark matter, the elegant dance of merging galaxies, or the ancient echo of the universe's first sound? Share your thoughts in the comments below and subscribe to continue this incredible journey of discovery with us.